In Hunan Province, engineers built a bridge rated to carry a fully loaded truck, and the deck under those wheels was made from grass, not steel. Not a steel-reinforced anything. Compressed, engineered bamboo capable of withstanding pressure past 3,000 psi, stronger pound for pound than the structural steel bolted into most highway overpasses. You heard that right. A material engineers dismissed for 100 years as fit for huts and scaffolding is now rated to hold up a truck. Let me tell you what that actually means in plain English. The walls of your house may soon come from a plant that regrows itself in under a decade, and that is just the beginning. If that sounds impossible, hit a quick like and subscribe so you do not miss the next one, because by the end of this video, you will understand exactly how a plant nobody respected became one of the most serious building materials on Earth. And the strangest part of this story starts nearly 40 years ago, in a lab nobody was paying attention to. For 10,000 years, timber set the ceiling on how fast humanity could build. A tree strong enough to frame a house needs between 25 and 75 years to mature, and that number is not a guideline, it is biology. Plant a tree today, and your grandchildren might be the ones who finally get to build with it. Cities do not wait that long. Populations do not wait that long. So sometime in the last century, the construction industry made a quiet trade. It walked away from timber's patience and turned to steel and concrete. Instead, materials that could be poured and welded on the builder's timeline, not the forest's. Here is the detail that puts everything into perspective. Steel and concrete production together account for more than 15% of all human carbon emissions every single year. More than the entire global aviation industry produces from every flight, every airport, every jet engine combined. That comparison should stop you. An industry built to shelter people is now one of the planet's largest single sources of the gas warming it. For decades, structural engineers accepted this as the cost of doing business. There was no third option. You could build slow and green, using timber that took a human lifetime to mature, or you could build fast and dirty, using steel and concrete that emitted enormous carbon for speed and reliability. Every architecture school, every civil engineering program, every building code on Earth operated inside that same trade-off. The consensus tracked by bodies like the International Energy Agency was always the same. There is no material fast enough to matter and clean enough to matter at the same time. Think of it like choosing between a car that runs on a fuel nobody can afford and a car that runs on a fuel that poisons the air. Both get you where you're going. Neither one is actually a solution. And for 100 years, that is exactly how the entire global construction industry operated, accepting a broken choice because nobody could see a third option on the table. Here's what most people get wrong about this story. The third option was not missing. It was sitting in plowed fields and hillsides across half the planet the entire time, dismissed so completely that almost nobody in serious engineering circles bothered to test it properly. What changes everything here is not a new invention. It is an old plant that everyone had already decided was not worth taking seriously, and the reason they dismissed it was not stupidity. It was precedent, decades of failed attempts that made the dismissal feel earned. That precedent is exactly where the story picks up next. Bamboo is not a tree, it is a grass, the same family that fills your backyard, only scaled up to something almost unrecognizable. That single fact is the reason engineers spent a century underestimating it. Some species of bamboo can grow more than 3 feet in a single day, a growth rate so fast you could stand and watch the stalk visibly rise if you had the patience to wait. While timber crawls toward maturity across decades, bamboo reaches full structural height in 6 to 9 years, an entire generation faster than the trees it could replace. And because it is a grass, cutting a stalk does not kill the plant. The root system stays alive underground and sends up a new shoot without any replanting, without bare hillsides, without the years of recovery a clear-cut forest requires. Pound for pound, raw bamboo can handle more tensile stress than structural steel, and builders across Asia have known this for thousands of years, using it for scaffolding on buildings dozens of stories tall. Here's what most people get wrong about this story. Bamboo's failure was never about strength, it was about consistency. A stalk is hollow, which makes it almost impossible to fasten 2 pieces together with any reliability. It is round, which fights against every flat, square, load-bearing system modern construction is built around. Drive a bolt through it, and it splits along the grain instead of holding. Leave it untreated, and it rots within a few years, inviting insects looking for an easy meal. And this is the detail that mattered most to the people who approve buildings. One stalk cut from a bamboo grove could test twice as strong as another stalk cut from the exact same plant, days apart, same soil, same rainfall. No inspector can approve a structural material that behaves like a coin flip. A building code exists to guarantee a beam performs, identically whether it is installed in freezing cold, scorching heat, or 30 years from now. Untreated bamboo could not promise any of that, and so the engineering world gave it a name that stuck for 100 years, the poor man's timber. Good enough for a hut, never good enough for a city. They said the same thing about carbon fiber before anyone figured out how to weave it into something an aerospace engineer would trust with a human life. We all know how that ended. For nearly a century, bamboo sat exactly where that dismissal put it, ignored by anyone with a structural engineering license. But the fix that eventually arrived did not come from finding a better species of bamboo growing somewhere in the world. It came from an idea nobody in the industry wanted to take seriously. Stop treating the stalk like lumber and start treating it like raw material instead. That single shift in thinking is where the real engineering begins. Here is the problem with treating bamboo like a tree. Every single flaw engineers hated about it comes from one decision: cutting a hollow, round, uneven stalk and trying to use it whole, the same way you would use a plank of oak. What if you never use the stalk at all? Picture a wheat field. Nobody builds a loaf of bread out of a single stalk of wheat standing upright. They crush it into flour first, then rebuild it into something completely different. That is the exact leap that turned bamboo from scaffolding material into structural composite. Engineers took whole bamboo stalks and ran them through machines that crush and tear the fiber apart along its natural grain, an industry step now called fiberizing. Picture the stalk being torn apart under steel rollers, the fiber unraveling into loose, stringy strands, closer to rough straw than to wood. Here's what most people get wrong about this step. The moment the stalk stops existing as a stalk, every one of its weaknesses disappears with it. There is no hollow center left to fight against. No round shape working against flat, square construction standards. No single weak point where a bolt could split the material down the middle. From there, workers dry the loose fiber and soak it in a specialized resin so everything can bond together under pressure. They align every strand in the same direction, then press the fiber mat under extreme heat and force, driving out nearly all the trapped air inside until the mat compresses down to a fraction of its original thickness. The result is a dense, uniform block, heavier than water, harder than most hardwood flooring sold today. A plant the industry once called too inconsistent to trust has been converted into something almost boringly predictable, batch after batch. And the waste efficiency here is the detail that stops most engineers cold. Roughly 80% of the original bamboo stock gets used in this process, including the bent, low-grade sections that would normally be discarded outright. Compare that to traditional lumber milling, where a significant share of every log is cut away and lost before a usable board ever reaches a construction site. This is not a byproduct of the process, it is the entire point of the process. A wild, unpredictable plant has been turned into a manufactured material with the consistency a building inspector actually needs to see. That is not a workaround. That is a completely different category of material. But a strong, uniform block sitting in a factory is not the same thing as a certified structural material an engineer can put a stamp on. That fight was never really about turning bamboo into fiber. It was about proving on paper that this fiber could survive the same load a beam of steel has to survive, and that proof turned out to be a far bigger mountain than the science itself. It sounds like it should not work. A grass pressed and glued back together, now outperforming premium engineered hardwood on paper. That is exactly why it does. High-grade bamboo Scrimber has been tested with compressive strength exceeding 23,000 pounds per square inch, roughly the load-bearing capacity engineers expect from mid-grade structural concrete, and bending strength, climbing past 43,000 pounds per square inch. Figures that sit comfortably above many grades of structural timber used in commercial construction today. Read that again slowly. A material once dismissed as fit. Only for huts is now beating the wood it was supposed to be a cheap substitute for. Here's the detail that puts everything into perspective. This is not some brand new laboratory discovery from the past few years. The first high-strength version of this process was developed in 1987 at Nanjing Forestry University, nearly 40 years before any of the structures built from it made global headlines. The chemistry has been sitting there, quietly proven for almost 4 decades. What changed recently was never the science behind the material. What changed was the ambition to actually build with it at real scale. Most people who read about engineered bamboo never get to this part of the story, the idea that the hard problem here was never chemical, it was institutional. A university lab can prove a material works in a controlled setting 100 times over, and that proof can sit on a shelf for decades if nobody with real capital decides to act on it. The resin bond, the fiber alignment, the pressing temperature, none of that was the bottleneck. The bottleneck was belief. Engineers had already accepted a mental model where wood grows slowly and steel gets poured fast, and there was no obvious slot in that model for a manufactured grass composite that behaves like premium hardwood. Breaking that mental model took longer than solving the underlying material science. That is the quiet, uncomfortable truth sitting underneath this entire story. The material was never the hard part, and once that mental barrier finally cracked, the material still had one more mountain to climb before any inspector would let it near a real building. A lab result and a certified construction material are two completely different documents, and the gap between them is measured in years of testing, not months of confidence. The next fight was not fought in a lab at all. It was fought in the quiet, unglamorous language of building codes. Here is the part that changes everything. Having a strong material sitting in a university lab does not change a single building on Earth. Plenty of brilliant materials never make it past the testing stage, filed away in journals nobody outside the field ever reads. The real gatekeeper, deciding whether bamboo scrimmer became a global industry or stayed a curiosity, was something that sounds almost boring: the building code. Codes move deliberately slowly and for good reason. Getting a structural material wrong is not a paperwork problem, it is a problem measured in collapsed roofs and failed inspections. An engineer cannot put an unproven material into a hospital or a school because one study says it seems promising. There has to be a verification layer, years of testing, agreed standards, and a paper trail any inspector anywhere can check and trust. For most of bamboo's history, that verification layer simply did not exist. And honestly, even today, there's a gap worth being honest about. When researchers recently studied companies manufacturing structural bamboo products worldwide, they found that only about 1 in 3 published clear, verifiable data on their material's actual strength, and fewer still held basic environmental certification. If you're an architect trying to specify this material for a real project, that gap is not a minor inconvenience. You cannot build something people will live and work inside using numbers nobody's willing to show you. But that gap has been closing, and closing fast. Engineered bamboo is now tested against the same international standards used to certify structural timber, run through the identical stress tests, moisture tests, and load cycles that every timber beam has to survive before certification. Think of this verification system the way you would think of a navigation app rerouting in real time. Every new study functions like another data point feeding the map, narrowing the uncertainty until the safest route becomes obvious to everyone using it. Nearly 7,000 studies on engineered bamboo were published in the 10 years leading up to 2024 alone, a volume of research most people who write about sustainable materials never even see referenced. That volume of testing is what actually moves an inspector's pen, not a single impressive number in a press release. Slowly, bamboo stopped being an interesting curiosity and became something engineers could put their names on official paperwork for. And once that confidence threshold was crossed, people stopped using bamboo scrimmer for floors and decking entirely. They started building things with it that no inspector on Earth would have approved just 10 years earlier. What they built next is where the real spectacle begins. Here is the honest picture, before we get to the part that actually shocks people. What follows is not a demonstration project or a lab prototype. In China, engineers designed and completed what is now recognized as the world's first 7-story building constructed primarily from engineered bamboo, with the columns, beams, and floors all built from prefabricated bamboo scrimmer components. 7 full stories, load-bearing structure included, made from a plant the construction world was calling a hut material 1 generation earlier. To put that in perspective, a conventional 7-story structure of that size would typically require well over 500 tons of steel reinforcement. This one replaced a meaningful share of that tonnage with a material that regrows itself before the scaffolding even comes down on the next project. And it did not stop at buildings. One engineer, working between research institutions in China and the United States, used engineered bamboo to build a road bridge in Hunan Province, rated to carry actual vehicle traffic. That bridge was assembled from prefabricated bamboo components by a small crew of workers in about 1 week, without a single piece of heavy construction equipment on site. A bridge made out of processed grass, strong enough for a loaded truck to drive across it, built faster than most residential additions get permitted. This is the detail that most coverage of sustainable materials never quite lands on. Engineered bamboo is not a decorative accent anymore. It is doing structural jobs that used to belong exclusively to steel and concrete, carrying real weight in real buildings that real people walk into every day. Here is the honest trade-off underneath all of this. That dense, high-performance bamboo scrimmer is held together with resin, typically a phenolic compound, and that resin is what gives the material its strength and water resistance. But it also means the finished beam is a composite, not a purely natural material, and open questions remain about long-term fire behavior, multi-decade durability, and what happens to that resin once a building eventually reaches the end of its life. None of that erases what has already been proven. It simply marks the honest distance between a certified structural success and a fully mature global industry. If a truck driving across a bridge made of grass surprised you, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover it. Because a 7-story building in one country is not yet a global industry, and what happens next depends on whether the rest of the world can catch up to what China already proved was possible. Construction is responsible for a staggering share of global carbon output, and steel and concrete alone account for more than 15% of it every single year, a number large enough that the sector's own emissions rival those of entire national economies. That is the scale of problem engineered bamboo is now positioned to chip away at. In 2022, the International Bamboo and Rattan Organization launched a global initiative aimed at positioning bamboo as a substitute for high-emission materials across construction and manufacturing. The following year, a national plan set concrete targets for scaling bamboo processing capacity, establishing demonstration zones meant to prove the industry could function at real volume, not just in pilot projects. That is the difference between an interesting material and an actual industrial shift. Here's what most people get wrong about how this spreads. Adopting engineered bamboo is not as simple as growing the plant somewhere new. It requires fiber processing plants, resin infrastructure, and hydraulic presses capable of the pressure and heat this material demands, the same kind of industrial base that took decades to build the first time around. A country with plenty of wild bamboo but no processing infrastructure cannot flip a switch and start producing certified structural beams overnight. Closing that gap is an investment problem, a training problem, and a standards problem, not a chemistry problem. This is not the first time an entire industry underestimated a material because the infrastructure to use it did not exist yet. Carbon fiber sat outside mainstream aerospace and automotive manufacturing for years, dismissed as too exotic and too difficult to produce at scale, until manufacturing infrastructure finally caught up to what the material itself had already proven capable of doing. Standards bodies and manufacturers are now responding to the same kind of demand with engineered bamboo, publishing verification data, and pursuing certification at a pace that would have been unthinkable a decade ago. The genuine advantage here is not a patent anyone can license overnight. It is the accumulated manufacturing know-how, standards infrastructure, and decades of testing data that cannot simply be copied. The same kind of advantage that quietly separates a promising material from a global industry. And if the same underlying pressure, a construction sector desperate for materials that solve the emissions problem without solving it by simply building less, is something you find genuinely fascinating. I already covered a separate breakthrough tackling the other half of that equation directly. It is called China's insane breakthrough just replaced concrete. Engineers are shocked. And what engineers found there is just as hard to believe as anything covered in this video. That one is worth your time. Here is the meaning underneath everything you just watched. For 10,000 years, building bigger meant cutting down something that took an entire human lifetime to replace. For the first time in that entire history, there is a serious structural material that fully regenerates before a child born today even finishes school. That is not a minor efficiency gain. That is a fundamentally different relationship between construction and the natural world, one where building does not have to mean permanently subtracting something from it. If you made it this far, you now understand more about engineered bamboo than most people who write headlines about green construction ever bother to learn. What was actually proven here is simple to state and difficult to overstate. A plant dismissed for a century as too inconsistent for real engineering was broken down to raw fiber, reassembled under heat and pressure into something stronger than the hardwood it replaces, tested against the same standard steel and timber have to pass, and used to build a 7-story structure and a truck-rated bridge in the real world. Not a claim, not a projection, a built, standing, load-bearing fact. If this changed the way you think about the walls around you or the bridge under your tires, hit that like button and subscribe so you do not miss what comes next. Now I want to hear from you in the comments. Does a manufacturer in Hunan Province, engineers built a bridge rated to carry a fully loaded truck, and the deck under those wheels was made from grass, not steel, not a steel-reinforced anything. Compressed, engineered bamboo capable of withstanding pressure passed